Good evening. Now that we are in the gravitational wave side of things, I'm going to talk about searches for continuous gravitational waves for neutron stars. My name is Anjana, and I'm a PhD student at the MPI in Hanover. 2 weeks ago, I submitted my PhD thesis. I will be telling it at the end of next month. In these years, my searches for CW signals have been dependent on pulsar astronomy. So I want to talk about how these multi-messenger type of CW searches work. And I want to do that by first introducing a few key concepts and then delving into the method with an example, and then finally wrapping up the whole story. Continuous gravitational waves are persistent, nearly monochromatic gravitational wave signals, which are emitted by neutron stars, because when a neutron star has a non-axis symmetric distribution of mass, and it rotates around an axis, this results in the time-varying quadrupole moment, which is all you need to generate gravitational waves. And we parameterize this non-axis symmetric distortion in terms of the ellipticity of the source. A CW signal is very simple. It's a simple sinusoidal signal at twice the spin frequency of the neutron star. And as I said, it's nearly monochromatic because the source is continuously losing energy. And also there's Doppler modulation due to the relative motion between the observers and the source. Here's an example of an expected CW signal. You can see the evolution of the frequency of the signal over time. And the large evolution that you see is due to the annual motion of Earth around the sun, and the detectors are on Earth. And in the inset, you can see the effect of Earth's daily rotation. We've not detected a CW signal yet. And our searches for these signals can be broadly classified into the all-sky or the blind searches, where we don't know anything about the source, and we look for signals from everywhere in the sky, having all kinds of spin parameters. And as you can imagine, these are really expensive computationally because you have to do a wide parameter search. Up the ladder in terms of sensitivity are the directed searches, where you expect a source at a certain sky position, maybe because a supernova exploded there, so you expect a neutron star there, but you don't know much else about the source. So those are the directed searches. And then you have the targeted and the narrowband searches, which are possible because some of these neutron stars are observed as pulsars, because you have these pulse emission of electromagnetic radiation, and that comes once per spin rotation of the neutron star. And when you time these pulse emission, you learn a whole lot of information about the source, using which I can build a template for the gravitational wave that it would emit, and then combine the gravitational wave data and search for this template. So that's what I do, and now I'm going to talk about the details of that with the example of this pulsar J1526, which is a Trapoon pulsar. It's also my latest search publication, and most importantly, it's a very non-complicated pulsar to search for, so I can say the story quite in an easy way. So once I have the pulsar, I first set up the template for the CW signal. The CW signal is parameterized by the spin parameters. As I said, it's at twice the spin frequency. So when I know the spin frequency at a certain reference time, I can know what it would be in another time during which I have the data. And the sky positions are known from the timing solution, so I know the Doppler modulation at every time. And if the object is part of a binary system, then I also search for the orbital parameters of the system. So in this example of this pulsar, here's the timing solution that Colin gave me. And here is my gravitational wave search parameters. So I have a signal at 800 Hertz, which is a very nice frequency to search at. And the spin down is a little bit low for my taste, but that's not surprising for a millisecond pulsar. And so once I have the template, I have to look at the LIGO data. At 800 hertz, the detectors are fairly quiet, so I don't have to do a lot of detailed noise analysis, but usually that's a step that I have to take care of. And the fact that the timing solution brackets the LIGO O1, O2, O3, these are all the observation runs that have been done so far, means that I can like combine all these data sets and look for this one template. So this means that I get the maximum sensitivity for a search that's possible by the data today, because this is all the observation runs we have so far. So the next step is to do a search. What is a search really? A search is asking the question, what is the likelihood that a data is a combination of a signal that is defined by the template that I mentioned before, and Gaussian noise, versus the likelihood that the data is purely Gaussian noise. And so this question is answered by the detection statistic that we call the F statistic. And we know its behavior in Gaussian noise. So once the search returns a detection statistic, we can quantify its significance based on the expectations in Gaussian noise in terms of a p-value. So for this pulsar J1526, this plot contains a lot of things, but it's basically a distribution of the detection statistic. The gray line is the search result, and you can see that with respect to the distribution for Gaussian noise, this is like fake, simulated Gaussian noise, or in terms of the theoretically expected distribution, the result lies very much in the bulk of the distribution, and so it's with a p-value of 29%, it's consistent with not seeing a signal. But it's dangerous to stop with a single template search because we're assuming that we know everything about the signal with that. So we always do a band search in the spin parameters to sort of acknowledge the possibility that there could be mechanisms which cause the electromagnetic and the gravitational wave signals to decouple. And we probe this fraction of 4.4% fraction of the gravitational wave frequency. And once again, with the results, we say significance, we coded significance based on Gaussian noise p-values. It's a lot of details, which I don't want to go into right now. But I can show you the example of J1526. We probed 3.2 hertz around this signal frequency, and I show here the cumulative distribution of those results. In the red line would be the expectation from Gaussian noise, because the p-values in Gaussian noise would have a uniform distribution, and then the cumulative distribution would be a straight line. And you can see that all our results are consistent with what's expected from Gaussian noise. If there was a significant result, it would come up as a peak in the low p-value region, which we don't see. So in the absence of a significant result, we move on to set upper limits on the strength of the continuous gravitational wave. What we're doing here is that we want to state with some confidence that the CW emission from this pulsar is weaker than a certain value, based on the fact that we didn't see a louder or higher detection statistic. So given our detection statistic, what does this mean about the emission strength? So to answer this question, we do a large number of Monte Carlo studies. We simulate signals from this pulsar with varying higher and higher amplitudes, and see what value of the amplitude gives us the fraction of injections that are recovered with to a value that's higher than our search result to be our, whatever confidence we want to assign to that value. So for example, in this case, you have the increasing amplitude of the signal, the fake signals from the pulsar, and the detection efficiency, which is really the fraction of injections, a fraction of simulated signals that were recovered with the detection statistic greater than our search result. And then you can read off whatever confidence you want. You can read off this plot. So in our searches, we usually report a 95% confident upper limit. And this 95% confidence upper limit then translates into a constraint on the ellipticity of the source, which was, to begin with, what source the gravitational wave. And that's the value of the ellipticity that we report. And for millisecond pulsar, it's usually the case that we get such low ellipticity values. So to summarize, I have shown you how, in the example of this pulsar, we do a continuous wave search when we have a tiny solution for a pulsar. And we always first start with a single template search around the signal frequency at twice the rotational frequency. And then we do a band search. When we don't detect a signal, we set upper limits on the amplitude of the CW signal. And this is then constraint on the ellipticity of the pulsar. Now you could do more fancy things like set upper limits in the band search, because we also did that. We do that when we have like a more promising pulsar. And now we have also a new Bayesian pipeline to do this, which I'm not going to talk about because it's a whole other topic. So I hope I have convinced you that this is a good thing to do, and we should continue doing this with the tiny solutions that you guys get with pulsars.
Right. So how would you select, which criteria will you use for saying, okay, this is a promising source? Because with all these telescopes, we're finding so many, right? Even so many binaries.
Yeah, so I want to start by saying that right now I don't choose pulsars. Like if it lies in LIGO's sensitivity frequency band, which is from 10 Hertz to 2000 Hertz, I would search for it. Okay. Because right now we have not made a detection, so we will look for all pulsars. But that said, you have something called the spin down upper limit for the pulsar. So if you assume that all the rotational energy that the pulsar loses is converted into gravitational waves, it's not true. But if you assume that, then you get a value for the CW string. So we can compare this spin down upper limit with the upper limit that we can, hope to achieve with the data that we have. And so if these two values are close, or if we can go below the spin down upper limit, then that's a promising pulsar. And if it's close by, or if it spins very fast, these are all good reasons to look for it.
I was thinking about your ellipticity of 10 to minus 8. So if I have 10 to 4 meters, that means it's about 10 to minus 4 meters. So 100 micrometers. So you're excluding the bump in the surface of the Newton star that's about 100 micrometers tall. Is that correct?
I did not really follow the math that you said, but
so the electricity means that any deviations are for the 10 to minus.
No, it's a ratio, right?
I think some people say that when you have 10 to the minus 9 of electricity, you are considering like a mountain of a fraction of a millimeter. So maybe you are up around this.
It's correct. That's talking about 0.1 millimeters. Yeah. So.
Okay. Thank you, Jim.
Yeah.
And back there.
Have you tried some sort of stacking analysis of all the pulsars?
Yeah, some people have done that some time ago, actually. You can look at Cutler and Schitt's paper, and they didn't find it to be very promising. I don't remember the exact details, but people have tried to do this.
So one of the promising mechanisms for the emission of gravitational waves from neutron stars is this F modes, which will output the gravitational waves at 4 Hertz.
Yeah, R modes, you mean? Yeah.
It's not in zero. So are you searching the actions against the frequency?
Yeah, we have somebody in our group who does R mode searches. I think when a pulsar glitches, afterwards for a while, it's expected to emit R modes. So it's mostly expected in young pulsars, which are glitchy, so I don't really look for those 4/3 effort. But then there are searches in our group as well as in LBK who, yeah, do that.
Are you looking also to longer period pulsars, not just, I mean, the emission of gravitational waves is most efficient if you look to millisecond pulsars. Because emitting of gravitational waves is to the fourth power of the rotation.
Yeah, that's square of the
Frequency,
rotation frequency. But yeah, no, we also look for young crab or whale like lower frequency are the most. The other pulsars for which they have beaten spin down upper limit. And so young pulsars seem to be also.
I mean, they are glitching much more often.
Yeah.
And a pulsar which was recycled, you may expect that also material which was accreted is all distributed equally over the surface.
I know.
But if you have a neutron star from a core collapse, there may be something electrical eccentric.
Yeah, there are a lot of ways to argue about it. But when you have these young pulsars, there's a high spin down value. So the F dot is high, and it seems that somehow you can go below the spin down upper limit with these pulsars. So I agree that for a recycled pulsar with the accretion having the possibility during its evolution, there's a better chance that it has a. But then these are also old pulsars. This might be. It might have had a chance to anneal that electricity as well.
But I mean, do you have an upper limit for the crab or for Vita?
Yeah.
And is it at the same level?
You mean the electricity values?
Yeah.
No, it's not. It's high. It's a high value that a neutron star crust cannot be expected to sustain. But that's also the pulsar for which you've gone below the theoretical upper limit. So you're able to actually say what fraction of the energy is actually converted into gravitational as an upper limit.
Mhm.
So the thing is that when we have an upper limit that's physical because it's lower than the theoretical upper limit, the electricity is such that it's too large that the strain it cannot be sustained by the star. And when you have really low electricity, we are not below the theoretical upper limit in terms of the strain. So it's, that's the story right now.